In this video, we'll take a look at a couple of examples of working with the uniform probability density function and along with the expected value and standard deviation. So we've already established that a uniform distribution is one that has constant probability density over an interval from A to B, where A and B are just some real numbers, and that horizontal line will be modeled by 1 over B minus A. The average value of that will be halfway between the beginning and end point, and then the standard deviation will be this less intuitive number here. So let's actually see an example of this. The amount of time in minutes that a person must wait for a bus is uniformly distributed between 0 and 15 minutes inclusive. So in other words, we're saying here is that between 0 and 15 minutes, that we have an equally likely chance of the bus coming anywhere along that interval of time. So we're going to see something that looks like this. And that means that since we know the area of this is equal to 1, this function is going to be modeled by 1 over B minus A, that's our probability density function, which is 1/15. And you can just verify that if you take length times height, or width times height, 15 times 1/15, the area under this curve needs to be 1. Now, we want to find the probability that a person waits fewer than 12 and a half minutes. And as we can see, this number is not, it's not in the middle, it's closer to 15 than it is to 7.5, which would be the middle. So what we're looking for is well, what's the area to the left of 12 and a half? And we can probably do this intuitively. We can probably see that 2.5 is the difference between 12 and a half and 15, and 2.5 goes into 15 6 times. So we would probably say that this area is going to be 5/6, or approximately 83%. But let's go ahead and do this using the idea of areas under the curve. So we want to find the area from 0 to 12 and a half under the function 1/15. Now the antiderivative of a constant is the constant times x. And in other words, what function has 1/15 as its rate of change? Well, it's going to be 1/15 x. And now we want to evaluate this on the interval from 0 to 12 and a half. So what do? Well, we can plug in the endpoints and subtract the evaluations at those endpoints. So we have 12 and a half 15ths, and lo and behold, 12 and a half 15ths comes out to about 0.833. So that's equal to 83.3%. So there's a pretty good chance that you're not going to have to wait the full 15 minutes. There's an 83.3% chance that a person waits fewer than 12 and a half minutes. But we might want to ask, like, well, on average, how long must a person wait? If I go there every day and I kind of kept track of how long I waited, and I recorded it and then took the average of all of my wait times over the course of, say, a week or a month, what would that be? Find the mean, mu, and the standard deviation, sigma. So mu is the expected value of x, sigma is the standard deviation of x, and so to find the mean, mu is going to equal a plus b over 2, which is 0 plus 15 over 2, which not surprisingly is going to be a 7.5 minute wait time on average. And that should make sense because it's equally likely that you wait any time between 0 and 15 minutes. Now sigma is going to be, the standard deviation will be the square root of b minus a quantity squared divided by 12. So this is going to be 15 minus 0 squared. 15 squared is 225 divided by 12. So the square root of 225 divided by 12 will give us our answer. And that's about 4.33. So this is still in minutes. And we could say something like this. On average, the wait time will vary by about 4.33 minutes from the mean. So there's a pretty good chance it'll be somewhere between 3 minutes and say 11 minutes, more so than it will be 0 and 15 minutes. So usually, on average, we're going to be pretty close to that, within that interval. Now we can also answer more intricate questions, like 90% of the time a person must wait falls below what value? 90% of the time a person must wait falls below what value? Well, we know that 83.3% of the time, wait time is going to be 12.5 minutes, but we want to know 90% of the time, what is that? In other words, what would this line right here be? What would this value of x be, such that the area to the left of it is 0.9? So we're kind of asking this question in reverse. Here's my function. Here's time 15. Here's time 0. This is my density function, which we know is f of x equals 1/15. And we want to find this value right here. We want to find this value of x such that this area is 0.9. Okay, well, normally the way we would find this, we would say the area from 0 to some point x, and maybe rather than using x, I'll use t, because x is the variable here. So from 0 to t, the integral of 1/15 dx, we want that to equal 0.9. So we need to solve for that value of t. Now, nothing's going to change here relative to what we did in part A. This is still 1/15 x. It has to get evaluated at 0 and t, and then that result will equal 0.9. So we'll do 1/15 t minus 1/15 of 0 equals 0.9. This is going to equal 0, so we have 1/15 of t equals 0.9. And now we can just multiply both sides by 15, giving us t is equal to 13.5 minutes. So there's a 90% chance you're going to wait fewer than 13.5 minutes, which makes sense because 83.3% of the time you're going to wait less than 12.5 minutes. So to get to 90%, you have to kind of add a little bit of potential time onto that. All right, that's some of the basics of working with a uniform distribution. Let's take a look at one more example. The total duration of baseball games in the Major League in the 2011 season is uniformly distributed between 447 hours and 521 hours inclusive. Find A and B and describe what they represent. Well, the times are uniformly distributed between 447 hours for the total duration of games, and the maximum is 521 hours. And what do they represent? Well, they represent the lowest total duration and the highest total duration. And they represent the endpoints. In other words, no total duration of baseball games is under 447 or greater than 521. Okay, now for this distribution, we need to ensure that this is uniformly distributed. So our random variable x which will be the total duration of baseball games, is going to, X will be distributed uniformly over the interval 447 to 521. So that's what we mean by write the distribution. Indicate how that variable is distributed and write it in a compact form. Let's find the mean and standard deviation. So we know that the mean, the average total duration of baseball games will be A plus B over 2, which is 447 plus 521 over 2. So if we take 447 plus 521 divided by 2, that equals 484 minutes. So the average total duration of baseball games. I imagine this probably maybe means for each team across the entire season. So if we take a look at like Arizona Diamondbacks, for example, my guess is this would mean that they play a total of between 447 hours and 521 hours. So that's the average time, and then how much do game times on average vary around that? Well, that's going to be the square root of, from our formula up above, B minus A quantity squared over 12, which will be 521 minus 447 squared, which is 74. 74 squared is 5,476 divided by 12. So we'll take the square root of that, 5476 divided by 12, and we get about 21.4 hours. So you can kind of imagine it this way. You have your 447 to the max of 521 hours. 484 hours is the mean. And then you're going to get some variability, some typical variability. So a lot of that variability will be between negative 21.4 hours of this and positive 21.4. Again, it's just a measurement of how spread out they are, how spread out the values are. But not surprisingly, you kind of notice that 21.4 is almost splits that difference between the low and the high. Okay, what's the probability that the duration of games for a team it is for a team. For the 2011 season is between 480 and 500 hours. Okay, so we've got enough experience in this now to say that we know that our distribution is from 447 to 521. So from 447 over here to 521. Now we have to get a function for this distribution. This is going to be 1 over B minus A, 521 minus 447. So this interval is 74 units long. And so again, if you take the width times the height, 74 times 1 over 74 gives you the area of 1 underneath this. And again, this is times here. I'm not going to label all the axes just for the purpose of making this efficient. And we want to know, what's the area between 480 and about 500. So we want to know, what is that area right there equal to? So the area between 480 and 500 of the function 1 over 74, well, you might notice that when we take this integral, we have 1 over 74 times x, and then that all we're really doing is we're looking at this function evaluated at those two endpoints, which is going to give us 1 over 74 times 500 minus 480. So you almost don't even need to really do calculus. You just need to know how far apart those 2 points are, which they're 20 units apart, and that represents an interval that is 20 units wide divided by an interval that is 74 units wide, and that comprises about 27% of the entire area. Okay, what is the 65th percentile for the duration of games for a team for the 2011 season? So 65th percentile is that same idea of asking, well, 65% of games are lower than what time? So here we have 447, we have 521, and I wonder if we can do this without calculus. Let's see. 65th percentile is going to be a little bit greater than half here. It's going to be some value x. We'll call it t again. And we want this area to be 0.65. Now, what we know is that this will be the integral from 447 to some value t of 1 over 74 dx. And in the end, we want this to equal 0.65. Now, we already kind of know how this evaluates. It's going to be 1/74th times the distance between the upper and lower. And so that will just be t minus 447 divided by 74. And we want that to equal 0.65. So I've just saved having to do maybe 1 or 2 steps here. And now I can solve for t by multiplying by 74. And then adding 447. So I get t is equal to 495.1. So that means I can say that 65% of total team games will be less than 495.1 hours.